Hi everybody, today we are going to do a pretty quick video, pretty nice and easy example from, again, the same electromagnetism textbook. This is chapter 23, example 7. We're going to move on from the continuous charge distributions and we're going to do a problem on Gauss's law. So here's the problem. Find the electric field at distance r from a line of positive charge of infinite length and constant charge per unit length lambda. So what we have here is an infinite line. You can think about this as like a wire, and it has some total charge, and they just give us the charge density lambda. So in this case, notice you can't really do any kind of total charge divided by length because the total length is infinity. It's an infinite charged wire, infinite length charged wire. So this is a problem for Gauss's law. And the reason this is a problem for Gauss's law is, well, take a look at my Gauss law video and see the introduction I do there. But you will see how this problem can be solved very easily if we recall the equation for Gauss law. So this is normally the equation associated with Gauss's law. It is an equation talking about the electric flux going through a closed Gaussian surface. So this is a Gaussian surface, and it gives you the electric field over that Gaussian surface, and all you have to know is the charge enclosed by the Gaussian surface. So if that didn't make any sense, just check out the Gauss law video. I do a bit of a more detailed explanation there. The problem I'm doing today is just solving this example here. So what we're going to do here is create the Gaussian surface, and your choice of Gaussian surface is, it's up to you, but you want to choose it in a kind of special way such that you can find the electric field at the point in question. So here we're looking for the electric field at a distance r. Let's say that is this distance over here. So this distance is a distance r, and we are looking at the, we're trying to find the electric field at that point there. So what we're going to do is actually create a Gaussian surface that is going to symmetrically cover this charged wire. And the Gaussian surface I'm choosing is like this cylinder that kind of encapsulates the rod. And the reason I'm doing this is, one, it's symmetric. So what you could say is the electric field lines coming out of this rod are going to be coming out in a direction like this, and also downwards. So let's say we cut the wire over here with a knife, and we look at just the cross section of the wire. Let's say this is the cross section of the wire, and the wire continues maybe down that way. The electric field, since the wire is positively charged with a, it has a charge per unit length lambda, so this is a positive charge density. The electric field is coming out of the wire in radial directions like this. So if you're looking at the wire head on, or head on from the cross section, it'll look like this. But if you're looking at the wire on the side like this, then you will see the electric field just coming out like this. Maybe you'll see some electric field lines coming out directly at you, and some other electric field lines going kind of backwards into the screen. Okay, so I'm going to choose my Gaussian surface to be this thing over here. And what I will do with Gauss's law over here is I'm going to solve this side of the equation first. So this Q enclosed is the thing that I'm looking for. What is the charge enclosed by my Gaussian surface? This is the Gaussian surface. So what is the charge inside this Gaussian surface? That is Q inside. Well, how we can find that is by doing lambda times the length of my Gaussian surface, right? Because lambda has units of charge. So this is coulombs per length. And if I multiply this by the length of my Gaussian surface, in this case it is a cylinder, then what I will get is an equation for the charge inside of this, inside of my Gaussian surface. So what I will do is label the Gaussian surface with some length L like that. And then I can answer this side of the equation. So I'm gonna write this over here, equal sign. All I have is Q enclosed is lambda times L. L is a new variable I'm bringing into play. It is something I'm defining, which is the length of my Gaussian surface, right? We can also talk about the radius over here of the Gaussian surface, and the radius is R. And I specifically chose that because the question is asking me for the electric field a distance R away from the wire. Okay, so the right-hand side of Gauss's law is solved. Now, what we're looking for here, this integral, if you remember, this is basically telling you to find the flux going, the electric flux going through the Gaussian surface, and this integral is telling you to add up all of the electric flux, through the Gaussian surface. So one interesting thing about the Gaussian surface that I chose here is that these side surfaces, they will contribute a flux of 0. So these little shaded areas, the flux of those, the electric flux, is going to be equal to 0. And the reason that's the case is because the electric field, so you see how here there's a dot product? This is the electric field, which is the thing in red. And this little dA is going to be the vector that is normal to the Gaussian surface. So on the cases on the side, the dA vector is pointing out like this. In the case on top, the dA vector is pointing right out here. On the bottom of my Gaussian surface, the dA vector is pointing out here. And if you can imagine, you know, this kind of cylinder shape also wrapping around in front of the wire, you will have also dA vectors over here pointing out towards the screen. And then also, if you imagine the back side of the Gaussian surface, maybe I should draw it with dotted lines like this. This is the back side of the Gaussian surface. You will have electric field lines going into the page like that. So I'm going to erase all these things here to keep the picture a bit simple. But basically what I'm saying here is that these portions over here, I guess the top and bottom of my cylinder, they will have an electric flux of 0 because the electric field is not creating any flux on those pieces. The electric field is creating a flux over here, and we will get to that in a second. So basically what we have is the sum of all the little flux components of the electric field going through a Gaussian surface. So we have 0 from one side, 0 from the other side, and then the rest of the flux is going to be the electric field multiplied by just the cylindrical area here that I have not calculated yet. So the entire surface area of the cylinder except these little side things, right? So if you look at a cylinder, it is basically just a rectangle like this. Here we have the top side and the bottom side. And if you cut this cylinder like this and unroll it, basically you will just get a rectangular sheet like this. So imagine you take a toilet paper roll and cut it and then unroll it. So what we have here is just the height of the cylinder, and in this case I called it the L, the length. And over here what we have is the circumference of this circle. Circumference. Or sometimes they call it perimeter. And for a circle, the circumference is pi times 2r, or pi times diameter. But in this case, what we are given is r. So if you remember, over here we are given r, right? That is this distance over here. That is r. So that is given to us. And yeah, that is the circumference here. So the total area of this is going to be equal to, let's write it in this way, 2 pi r times L. Okay, it looks good. Now, if we take this area and we just multiply it in here, right, that gives us the total flux going through our toilet paper roll thing. That will just be 2 pi r L. Cool. Now take a look at this. We have L on one side, L on the other side. So that new variable that I introduced, it actually gets canceled out and it's not included in the electric field. These two zeros are not included, and Gauss's law basically gives us the equation for the electric field. So if you move this 2 pi r onto the other side, what we get is 2 pi r epsilon naught. On the top we have lambda. So this is the answer for the electric field. A distance r away from a charged wire with linear charge density lambda. One other thing I can say is, if you remember this Coulomb constant, it is actually defined as 4 pi epsilon naught in the denominator and 1 over here. So we can get this in the bottom if we multiply the top and the bottom by 2. That does not change the equation. And what that gives us is electric field is equal to 4 pi epsilon naught times r. In the top we have 2 lambda. And what we get here is Ke times 2 lambda over r. So this is two different ways to write the electric field. Both of them should be correct. And yeah, very quick video. I hope that was helpful. If my explanation of Gauss law didn't make sense here, again, please check out my other Gauss law video. I will try to put a link somewhere in the description or somewhere here. But yeah, very simple problem, very quickly done, and this is why Gauss's law is introduced in the same chapter as calculating continuous charge distributions, because if you can use Gauss's law, basically you just go from this equation and, you know, a bit of geometry and a bit of like sort of calculating the electric flux, and you can find the electric field in literally 2 steps. These are the 2 steps I did. So when you can use Gauss's law, it is very, very useful to use it. But there's only specific circumstances you can use it. So Gauss's law will not work for a finite length charged rod. Maybe you can create a Gaussian surface over here, and it can help you find the electric field a distance r over here, kind of like how we did it here. But the problem is, with a finite charged rod, the electric field lines in the center, yes, they are going further out, but as soon as you get to the edges, you get some kind of effect due to the edges like this. So these edge effects will ruin Gauss law, and they will make this integral over here much harder to solve. So this is why Gauss law only works with specific geometries. So if you had a very, very big wire, sure, you can use Gauss law. Just take the center portion of a wire and you can approximate the electric field here and here. But you cannot use Gauss's law here or here. I mean, technically you can if you had a computer and you could solve this problem, but it would be fairly complex. So I hope that was helpful. I'm going to do another video on some Gauss law problems, and then we're going to get into chapter 24, which is going to be a crazy one. Hope you guys enjoyed. Have a good one.